Okay, so today we're going to talk about the real number system and then a few of the properties. So some really basic things about numbers and things that we've dealt with for years. And so the real numbers consist of a bunch of other numbers. So the real number system is the numbers that we are used to dealing with. We will get into what's called the complex number system later on in this semester, and it adds another type of number to it. But the real number system are the regular numbers that we've been dealing with for years, doing math out of that. And the symbol for the real number system is just a big old capital R. Okay, so big old capital R there is what you want to write that as. So big capital R in that blank right there. And that's the symbol for a real number. We're going to use some abbreviations when we talk about these different sets. So the first type of number that is inside of the real numbers is what's called an irrational number. Irrational numbers, as you can read right there, are types of numbers in which the decimal form never terminates. That means it never stops, or it never repeats. So repeating decimals, something like 0.3 repeating, you remember the notation with the bar over the top of it, means that 3 keeps going forever. Those are not irrational numbers. Irrational numbers are numbers kind of like pi or the square root of 5, some weird numbers like that the decimal never terminates and never repeats. So irrational numbers are kind of a weird set of numbers. Pi, non-perfect square root, so square root of 5 is not a perfect square root, but square root of 4 is. So it's not an irrational number. So got to be careful when we look at that. We'll look at some examples as we go along today and start classifying some numbers. And then the rational number system, or the numbers in the rational number set, are numbers which the decimal form, it either terminates, stops, or it repeats. Rational numbers, look at the first 5 letters of the word rational. What word is that? Ratio. How do we write ratios normally in a math class? Yeah, we could write them with the colon, like 1 to 3, or write out the words 1 to 3, or we could write it 1, 2, 3. Or what's another way to write a ratio? As a fraction. So 1 to 3 could be written 1 over 3. Those are rational numbers. If a number can be written as a fraction, then it's a rational number. That's the whole idea of rational numbers. We'll do some stuff in this class with rational numbers. We'll do some things with rational equations and expressions. Just means fraction equations and expressions. That's all it means. So it sounds real fancy, but it just means numbers that can be written as fractions. That's all it really, the gist of that is. So inside of the rational number system, there's a bunch of other numbers. And these are the ones we're probably most familiar with: the integers, the whole numbers, and the natural numbers. And the natural numbers are the ones that came along first because when you learn to count, where do you usually start? 1. So you started at 1, 2, 3. You counted how many fingers do you have and all that stuff when you were a kid. That's how you learned to start. It was natural. That was the way things went. And then in the course of history, they started looking at, oh, what if you don't have anything? You had to have a 0. So the concept of 0 was added, and that became what's called the whole number set. So the whole numbers is really just the natural numbers and then add a 0 to it. That's the only difference in the natural numbers and the whole numbers. The integers adds in the negative side. And that's the only thing it adds in. So the rational number system includes all of those. They are inside of the rational numbers. And then, excuse me. I could make it today. May not be able to. So the rational numbers kind of fills in the gaps in all those. The fractions do, because those are the numbers in between all of those, right? So the rational numbers is all of these kind of numbers, these 3 sets, plus all the fractions that are in between there. Okay, so that's what the rational numbers are. So one of the best ways to, I think, show that is with this little diagram that's right below that. You've got this large box. So the big rectangle shape is the real number system. So these are the real numbers. That's the big box. It contains all of these other buckets is the way I describe it. So each circle inside is a bucket. And when there's a circle inside of a circle, that means that bucket is inside of another bucket. It's kind of like, what are they called? The Russian nesting dolls. Have you ever heard of those? For one, you take them apart and there's just a smaller version inside. So that's the same idea here. So the rational or the real number system is the big box. That contains everybody. This bucket right here is the irrational numbers. And we're going to abbreviate that with an I. And I'm going to scroll down right beside that on your paper. You see that chart? The irrational numbers, the letter we're going to use is a big capital I. And examples of that would be numbers like pi, the square root of 5, the square root of 72. A lot of square roots are in there. And there's a bunch more, like infinite number of those that we could find. But the irrational numbers are this kind of separate bucket over here. They're the weird numbers that we don't deal with a whole lot, but they come up. So we've got to have a name for them. So we call them the irrational numbers. Now, the largest bucket of those buckets inside of buckets, the biggest one, the biggest circle there on that is going to be the rational number set. The rational numbers, its abbreviation is Q, because we already used R for real, so we can't use that. But think about the fraction 7 over 3. 7 divided by 3. What's the answer to a division problem called? A quotient. What's that start with? A Q. So a fraction is really a quotient. So the Q for the rational numbers kind of makes some sense that it should be, use a Q there. There's also a Greek word for rational that starts with a Q, and I can't even for the life of me say it, so I don't spell it or anything like that. So rational numbers is going to be the abbreviation Q. And in the rational numbers, there's numbers that can be written as fraction or terminating or repeating decimals. So we might have something like 0.34. That's a terminating decimal. It could be written as a fraction as 0.34 is 34 over 100, right? And we could reduce that if we needed to, but it's a fraction. 1 5/8. It's a mixed number, but it can be written as a fraction, so doable. Let's use that bar notation. 0.3 repeating. That's a rational number, repeating decimal. -7 over 11. That's a rational number. It's written as a fraction. It happens to be negative, and that's okay. And there's a bunch of other examples of that. But here's the idea, is that big circle with the Q in it contains all of these circles inside of that. Okay, so it's a bigger bucket that's got everything else in it. Okay, now the next circle inside of that is going to be our integers circle. And the integers is going to be a big capital Z. I had a pretty good reason for the Q. I don't really have a great reason for Z, other than it's just a good letter that doesn't get used very often. So at the end, we felt sorry for it. We're going to use a Z to represent integers. So the integers are the positive and negative whole numbers and 0, right? So inside of that bucket, you're going to have numbers like 7, negative square root of 100. Why is that inside the bucket? It's got a square root in it. What's the square root of 100? 10. It's a nice number, right? So it's a perfect square number. So you can simplify that. So we got to keep in mind, we may have to look at some numbers and maybe simplify them a little bit in order to classify them, so we know what kind of number they are. You also have the number 0. 8 over 4. How is that an integer? Yeah, it's a whole number too. It reduces, right? So think about simplifying comes into play there. So the integers is inside of the rationals. And then inside of the integers bucket, there's another bucket. The next one inside of that is going to be the whole numbers. We'll use a capital W for the whole numbers. So the whole numbers is going to have the positive side of the integers and 0. So 0, 1, 2, 3, etc. Keep going. And you could have Square root of 16, 20 over 4. Those are also whole numbers. They're also integers. Here's the thing. As we're going further and further inside of the buckets, if you're in the inside bucket, you're also in these other buckets too. So if you're a whole number, you're also an integer. You're also a rational number. You're also a real number. Okay? You're not irrational because that's that separate bucket that's outside, right? The scrap bucket that we don't use, right? So when you're inside of the natural numbers bucket, which is the very smallest bucket, you got the numbers 1, 2, 3, technically square root of 9, 34 over 2, 47, just random examples of natural numbers. Only positive numbers, no zero. Okay, so the natural numbers, if you're in this bucket, then you're a natural number. If you're inside of that bucket, you're a natural number, you're a whole number, you're an integer, you're a rational number, and you're a real number. You're all 5 of those if you're inside of the natural numbers bucket. So when you classify a number, you're going to classify it as all of the things that it is. Okay, so if it's on an inside bucket, then it's got to carry all those other buckets with it. Okay, so let's look at some examples of classifying some numbers, and we're going to use these abbreviations. So your handout's got them right there above it. So we're going to use those abbreviations to name all the sets for each number that's listed here. So let's start with number 1, -10. So let's try to get it into the inside most bucket that it goes in. So what kind of number is -10? It's an integer because it's a negative whole number, right? So that's an integer. So we're going to call it a Z. But the integer bucket sits inside of what bucket? The rational bucket. So it's also a Q. But the rational bucket sits inside of what? The real numbers bucket. So it's a R as well. So this one is a integer, rational, and real. All 3 of those. Let's look at number 2. There's square root of 30. Does 30 have a nice square root? No, it doesn't. It's a decimal. Does that decimal repeat or terminate? Here's the thing. If it's not a nice square root, then no. Like if it doesn't come out to be a perfect square, like square root of 25 is 5. But anything else, like square root of 26 doesn't work out nice. Square root of 30 doesn't work out nice. Those are not going to terminate and not going to repeat. Square roots don't repeat unless it's of a fraction of some sort. So this one would be an irrational number. But because it's irrational, where does the irrational bucket sit? Inside of the real numbers as well. So it gets an R as well. All right. Let's look at number 3 there, the mixed number 1 7/9. Is that a natural number? No, it's not a count. We didn't learn to count 1 7/9, 1 8/9. So we didn't learn to count that way when we were little. So it's not a natural number. Is it a whole number? Definitely not. It's got that fraction in there. It can't be a whole number if it's got part of a fraction on it. So is it a integer? No. If it's not a whole number, and then it's not a negative, it's not an integer either. And it's a rational number because it's written with a fraction. Okay, so it's rational, which is a Q. And what else? Real. Guess what? Every one of them is going to be what? Real. Until we get a little further in the semester, and then we'll get into the complex number system. I'll talk about that. Teach you about that too. That's a few weeks out before we get there. So, all right, number 4, 24 over 8. What is the whole number? 3. That reduces to be 3, and then let's classify 3. 3 is a whole number. Is that the smallest bucket it goes in? It's a natural number because that's one of our counting numbers. So it's a natural number. and a whole number. Well, if it's both of those, then it's an integer and a rational and a real. So it's 5 of those 6 choices. Let's look at number 5, 2.48. It's what? Rational. So terminating decimal, so it's rational, and it's got to be real as well. What about number 6? Yeah, it simplifies to be -9, which makes it an integer. That's good. But if it's an integer, what else is it? Rational number and real. Never will you have Q and I on the same answer choices. Can't happen. Just doesn't work that way. All right, let's see if we can work on number 7. That looks weird. What is that? Pi minus pi. What's pi minus pi? 0. What do we know that pi is? Well, 0 is a whole number. I agree with that. But what's pi? Just while we're thinking about it. It's an irrational number. What do we normally use in the place of pi, like in a geometry class? 3.14 is a good estimate for that. But is that really what pi is? No, remember it has just tons of digits that keep going forever, never repeats, never ends or terminates out of that. So, so whole number, it's also a what? Integer, rational, and real. Yeah. Okay. This one's a little tough. It looks hard, but if you'll think just a little bit about square root of 16 and square root of 25, what is that? 4 over 5. Square root of 16 is 4. Square root of 25 is 5. So we're just doing the square root of the top and square root of the bottom. And 4/5 is what kind of number? It's rational because it's a fraction, and it's also real. Nothing else. What about 19? I mean, number 9. This the 15.15 repeating. So is this rational or irrational? Rational, because it repeats. That bar above it means that this is a repeating decimal of 0.15151515. It doesn't end, but it repeats. And rational numbers can be repeated. If you wanted to write that as a fraction, the shortcut is it's 2 digits repeating, so it'd be 15 over 99, and then you would reduce from there. That's the shortcut for doing that. So if it's rational, it also has to be real. That's all. Okay, that one would be. Number 10 is a little easy. Let's do that one. It was like an easy one to mix in there. 109. It's natural. We didn't. And if it's natural, it's also whole. So integer, rational, real. Good job. Number 11. Does that one simplify out? No, it doesn't. So what can it be? It's rational because it's a fraction, right? And then if it's rational, it's also real. And because it didn't simplify, it can't be any of those other things. Okay? So if you get a fraction, it's got to simplify some to be anything other than rational. Number 12. This one's a slightly tricky, maybe. I don't know. Maybe I'm overthinking it. What is that? It's 1. If you divide the same thing by itself, it's always going to be 1, right? So what's 1? It's a natural number, whole number, integer, rational, real. Good job. So being able to classify those numbers. This is going to come back up kind of throughout the semester. It's kind of one of those things that it was the way the course kind of works is I kind of spiral things back in throughout the semester. So this will come back up. Classifying numbers will just be, kind of seems like a random question, but as we add different types of numbers, we still got to be able to classify these other types of numbers too. So it'll come back up as we go through the semester. And so don't lose, we don't use this a whole lot, but don't forget it. You guys seem to have a good hold on it for right now. So that's great. Let's look at the properties. We'll try to get through these pretty quickly. And talk about the properties of real numbers. Real number system, when we're doing operations, there are certain properties that hold true for addition and multiplication that don't necessarily hold true for subtraction and division. But addition and multiplication, these properties here do hold true. So the commutative property, does anybody know what that does? That's the property of equality. But what does commutative property do as far as when I take a problem? Let's say we took A plus B. Commutative property says that this is also true, B plus A. What does that do? Swaps the order. Doesn't change the answer, though. If I add 3 plus 5, it's 8. If I add 5 plus 3, it's 8. So commutative property just swaps the order. Okay, so we got to know properties to help us when we're going along through here. So when somebody says something, use the commutative property of addition, that we know what that means out of that. So it just means swap the order, but the answer doesn't change. Okay, with multiplication, it's the same way because 2 times 3 is what? What's 3 times 2? It's the same answer, right? So A times B is equal to B times A. It's the same idea with the commutative property. So commutative property changes the order in which the problem is written, but it does not change the answer. That's what the commutative property of addition and multiplication do. The associative property, and these two up at the top, the commutative and associative, are some reason easily confused, but they're very different. The associative property has parentheses in it. The commutative property does not have to have parentheses in it to exist. The associative property does. The associative property of addition says that if we take two things and add them together and then add a third thing, that we can rearrange the order in which we do things by just moving the parentheses, but that won't change the answer. Notice that on the left side, it's A plus B plus C, parentheses around the A and the B. On the right side, it's still A plus B plus C, but the parentheses are around something different. It did not change the order the problem was written in. Commutative property changes the order the problem is written in. Associative property just changes what's inside of the parentheses. So know the difference in that commutative property changes the way it's written. Associative property just changes what's in the parentheses. So be careful of that. It's really easy to confuse those two because they're both changing the order in which you do the problem, but it's not changing the answer. So a lot of people get those confused. So on the multiplication side of things, it's the same idea. We're multiplying A times B and then multiplying that answer times C. If we change the parentheses, the order of operations tells us to do B times C first, right? Because parentheses comes first. And then multiply that answer by A. But it doesn't change the answer. It changes what order of operations says to do, where the commutative property just changes the order it's written in. So know the difference in those two out of that. Now, the next one, the identity property, that's probably the easiest one, but it's the one most people just don't remember ever talking about because we don't talk about it a whole lot. Identity means that with addition, what can we add to something and get the same thing back? 0. So the identity for addition is to add 0, and we get the same thing back. Easy, right? But we don't ever talk about adding 0 to something. Identity property means what can you do with that operation and get the exact same answer that you started with. Okay. With multiplication, what's the multiplicative identity? 1. So A times 1 is going to give me A. Okay. Identity means you get the same thing back. That's what identity means. All right. The inverse property, this is the one we've used, we use a lot when we're solving equations, which we'll do some of in the next week or so. We'll do a lot of in the next semester for sure. We'll solve a lot of equations. But the inverse, what's the inverse in? It's the opposite, right? So the additive inverse, what's the inverse of A? Negative A. I'm using parentheses there just to emphasize the negative sign, is that it's not a minus sign, it's a plus negative. That's the only reason I'm using those parentheses. They're not really necessary. What happens when you add A plus negative A? They cancel each other out, and you get a 0 right out of that. So the additive inverse is add the negative or the opposite of what you started with. What's the multiplicative inverse, or the inverse with the multiplication? How do you cancel out? That's the idea. We use the inverse to cancel things out. So how do you cancel out with multiplication? And here's the thing, you don't get a 0 when you cancel out with multiplication, you get a 1. So what times A will give me 1? And we don't usually call it the multiplicative inverse. We have another word that we use for it that starts with an R. I'm going to go down right below this, and I'm going to write an example of an equation that you all know how to solve. 2/3 x is equal to 5. How do you solve that equation? Okay, what's another way of dividing by 2/3 since it's a fraction? What is 3/2 called? The reciprocal. You flip it. So what's the reciprocal of A? No, that's the opposite of A. The reciprocal would be 1/A. Because there is an understood 1 underneath A. So the multiplicative inverse, fancy long version of saying reciprocal. It's the same thing. We've always called it reciprocal growing up, but it's actually called, in math, it's the multiplicative inverse is what it's called. But I'm fine with using the word reciprocal. But understand, multiplicative inverse is the same thing. Okay. All right. Last property is the one that bridges the gap. It combines addition, subtraction with multiplication. It's the distributive property. We all have done lots of distributive property over the years. A times B plus C. That number that's on the, or number or letter that's on the outside of the parentheses multiplies to everybody that's on the inside. So you get AB plus AC. That is the distributive property. Okay. So what we're going to do with those examples that are right below that thing is we're going to recognize what property that we're dealing with there and what operation it goes with. So we're going to name the property that's being used. So look at number 13. It says 5 times parentheses 2 times 8 is equal to parentheses 5 times 2 close parentheses times 8. Associative, because it has parentheses in it. Did the order of the problem change? No, it's still 5, 2, 8, right? The parentheses change. So this is the associative property. And then we'll put in parentheses MULT for multiplication. Pretty obvious it's multiplication, but I want you to put it in there, to make sure. All right, let's look at 14. Say it again. Distributive, that's right, because they're taking 6 times each piece on the inside. So yes, that's distributive property. And the good thing about distributive is you don't have to tell what operation it is. It only can be multiplication over whatever operation is there. So it's just distributive. What about 15? Inverse. What kind of inverse? Additive or multiplicative? Additive, yeah, because it's the opposite. And we'll just abbreviate that add. That's an easy way to do it. I'm not going to be too picky about that part. 16. Commutative. And then it's of addition because it's plus signs between there. So you need to learn to spell these because you're going to have to write them out on the quiz and stuff. So that's some interesting ways of trying to spell them. That was no way in, it wasn't even close enough to give partial credit on some of it. It was a whole different word. So learn to spell them. All right, 17. Associative. And be of addition this time because it's plus signs between it. 18. Look at that side. That's the side that matters. Be an inverse, right? Multiplicative inverse. Reciprocal, another name for that. I want you to kind of try to move over to the call it the inverse. 19. Distributive. It's written kind of backwards, right? They've got the distributive property written on the right-hand side instead of the left-hand side. But it's the same thing, right? So it's still distributive. Okay. 20. Identity. Good job. That's the additive identity. Pretty easy, right? All right, kind of help improve that inverse idea. Let's look at these 4 problems real quick and see if we can get the additive and the multiplicative inverse for each one of those. So that's all we're looking for, not really doing anything else to it. So what would be the additive inverse? Yes, positive 8. Good job. What would be the multiplicative inverse? Try again. Because how do we write negative 8 as a fraction? We put it over 1. The reciprocal of that would be flip it. That wouldn't change signs. Negative 1/8. Don't change the sign on the multiplicative inverse. The additive inverse changes signs. Multiplicative inverse does not change signs. It's the same. Bless you. Okay. 22. 2/3. Additive inverse would be negative 2/3. Just change the sign. Multiplicative inverse, reciprocal, just 3/2. That's all you got to do is flip it. And this one throws the variable in there, but it's negative 6w. Multiplicative inverse, 1/6w. And the w needs to be in the bottom. Make sure it's clear that that variable's in the bottom too. Okay. Don't put your w out beside it. Last one's got a square root in it. That's okay. Yeah, just put a negative sign in front of it for the additive inverse. The multiplicative inverse, flip that over, it'd be 1/√10. And that's all. I'm not going to make you rationalize that yet. We'll get to those plenty when we get into the complex number system. We'll do some rationalizing. Okay. All right. Last property of the day, last thing we're going to do, and then you'll have about 50 minutes here to work, is the closure property. Closure property, what it is it's talking about a set of numbers closed over a set under a certain operation. So when we're talking about a set is closed, that means whatever you start with, you're only going to pick numbers from that set. Well, so let's say we start with the integers. Whatever I pick for my problems, I'm only going to pick integers. If an operation is closed over the integers, then that means I'll only ever get integers back. I can't get anything else back. So let's look at these examples. It's really kind of example is the best way. Now it says if it's false, give a counterexample. A counterexample is just give me a problem that doesn't give me that kind of number back. Okay, so if we're talking about integers, give me a problem that doesn't give me an integer back. Just an example. A counterexample is just an example that shows what you're saying, the reason it's false. Okay, so integers, again, we know what integers are. What are integers? Negative and positive whole numbers, and then zero. So that's the kind of numbers we're dealing with. No fractions in integers, right? No fractions in integers. All right? Yeah, this is yes. Okay? That means that the fractions are not part of that. So when we deal with integers, we want to know, is it closed under multiplication? So if I multiply an integer times another integer, do I always get an integer back? Can we come up with a one that doesn't do that? Well, if I try some weird integer like negative 13 and another integer like 5, it's negative 13 times 5, an integer. Yeah, it's negative 65, so it is an integer. So it always gives me an integer back. The integers are closed under multiplication because we start with integers, we always get an integer back no matter what. Even if we take negative 5 times negative 2, that's a negative times a negative, that's positive 10, right? Positive 10 an integer? Yeah, so no matter what I do, if I'm starting with integers and I multiply them together, I end up getting integers back. So this one is true. It is closed under multiplication. 26 says irrational numbers are closed under subtraction. So what are the irrational numbers, or what are some examples of irrational numbers? Pi is a good example. Square root of 5 is a great example out of that. Now it says closed under subtraction, so that means subtracting. So if I subtract irrational numbers, do I always get irrational numbers back? Give me an example. If you're saying I can't, then you got to give me a counterexample. Well, that's a great example. Pi minus pi, that's two irrational numbers, right? Pi is irrational, pi is irrational. Subtract them, you get 0. Is 0 irrational? No, we know 0 is a whole number, it's an integer, it's a rational number, it's all of those things. It's real. This is false. Pi minus pi was the example that was given. And 0 we know is not irrational. Another example might be, you might do square root of 5 minus square root of 5. There's tons of counter examples for that one, but you only need one. You just need one case where it doesn't work and it's false. Okay. 27. Whole numbers are closed under division. So if I take two whole numbers and divide them, will I always get a whole number back? Give me a counter example if it won't work. I got to use whole numbers. Eight is a whole number. 4 is a whole number. What's 8 divided by 4? That's a whole number. I thought y'all said it didn't work. Can you come up with a counter example? I came up with an example that worked.
3 divided by 2, you don't get a whole number.
Oh, 3 divided by 2. 3 is a whole number, 2 is a whole number. But when you divide it, you get 1.5, right? Which is not a whole number. Right? So there's a good counter example. Good job. So this is false. Three divided by 2 equals 1.5. Not whole. And there's a good counter example out of that. That's great. Tons of other examples that you could use. All right. 28, it says odd numbers are closed under addition. What? You think they are? Okay. Oh, 7 plus 7 is 14. What kind of number is 14? Even, not odd. You just gave us a counter example.
Oh, so that means it.
So that means it's not. So this would be a false one. And I gave us a good example. 7 plus 7 equals 14, which is even. And that's why that doesn't work. 7 plus 5 is 12. There's another counterexample. 1 plus 3 is 4. So doesn't look like odd numbers are closed under addition out of that. Okay. So the closure property, you start with a certain kind of number and you have to get that kind of number back for it to be closed. If you can come up with a counterexample that does anything else, then it's false. And we write that counterexample down. Okay. That's the property that last semester's folks seem to have the most trouble with. So